There we go. With that, Shree, it's all yours.
Thank you. Thank you. Today, I'll be giving a brief overview of two packages developed within the Paton lab called DBStep and Acme. In general, like just with the overall goals of CCAS, like what was mentioned in the beginning of the call, the goal is to actually develop tools which can be utilized by the scientific community. And most of these tools are actually hosted on the NSF GitHub. I think Rob also posted a message saying if you want the tools that you've developed to be forked onto this, you should probably message him. These are mostly tools which are on here are completed, published tools or working and tested tools. I know that there could be other packages that have been developed within CCAS which are under development, but potentially, yes, could be hosted on this GitHub, which could be accessible for everybody within the scientific community. Today, I just wanted to highlight some of the tools that's been developed within our group. To name a few, as I have a bunch of small pictures on top right here, have been developed by previous postdocs, previous students who were part of CCAS, Lily and Julian. To specifically say about Julian's work, he kind of contributed to development of Good Vibes and the DBStep package, which are Python-based packages, could be used in Jupyter notebooks, could be used on the command line. Specifically, Good Vibes being a post-processing tools for a lot of computational chemistry output files, for example, and DBStep is something that I'll go over today. The other domain of tools that have been developed within the group corresponds to machine learning-based tools, where, for example, the Cascade web server, which is where you could plug in smiles to get out NMR, Boltzmann averaged NMR results for small organic molecules, and the other one being Alphabet, which is a bond dissociation energy prediction tool, which is hosted currently on the NREL webpage. Today, I will be talking specifically about two tools. Firstly, DBStep, which looks into quantification of molecular shape, and another tool called Acme, which has been developed over the last few years within the group called Automated Quantum Mechanical Environments, which is essentially very useful in developing workflows. Starting off with some background about why we're interested in developing tools, for example, like DBStep. Traditional cheminformatic methods have been where we use representations corresponding to 1D, which could just be, for example, the count of number of carbon atoms, number of rings, number of stereocenters to do some modeling tasks. But there have also been other 2D representations to, for example, move from atom-based counts to actually incorporating fragment-based structures into different kinds of descriptors, and specifically them being Morgan prints, which are kind of circular in nature. While these kind of encode 2D structure, what we're losing out here is information corresponding to, for example, non-covalent interactions, which could be obtained only if you look into like the 3D representations of the molecules. And there are various 3D representations of the molecules, which could be used, for example, the stereomole representations to quantify how long or how wide a molecule is. While these are 3D representations, there are other representations which are 4D in nature. But what I mean by 4D is multiple 3D geometries, which essentially constitute of an ensemble of molecular structures from which you could get Boltzmann average properties or min-max values for different, for example, stereomole could be a range as shown here on this scale. While we're generally interested in quantifying molecular shape, historically, steric parameters have been obtained from experimental values of, for example, macroscopic observations, which corresponds to relative rates of reactions, rotations of molecules, or the populations that a specific molecular structure is present in. While this has been done experimentally, more modern computational approaches attempt to capture, for example, the shape of the molecule. This could be, for example, just a 1D parameter, but no molecule is actually just completely circular. They are mostly multidimensional in the sense that it's not symmetric in nature, and we want to have a parameter which could, for example, quantify the size and the shape of the molecules in different directions, corresponding to how much of change is actually there in structural shape. And to do this specific task, one of the first works was done by the Sigmund lab, where they used these stereomole descriptors, such as L, which corresponds to the length of the molecule, B1 and B5, which corresponds to the length of the molecule actually in the perpendicular directions of L, to actually look at incorporating these stereomole parameters into reaction modeling. So in general, multidimensional parameters are required and are very useful in distinguishing molecules which have like more complex shape. To understand properties of, sorry, that was a bad animation, but to understand like quantifying molecular properties and shapes, there have been existing tools in the literature. Firstly, I talk about one, which is the ModRad tool, where we could actually look at utilizing this Python package to get 2D and 3D molecular features. Some examples of the 2D features or molecular properties that you get correspond to, for example, the adjacency matrix, which talks about how or what's the bonding information between different kinds of atoms in the molecule. This package also provides, it's based off of RDKit, but it provides Lipinski-based descriptors, for example, corresponding to a number of hydrogen bond donors, hydrogen bond acceptors, for example. And they do also have some molecular 3D features, for example, molecular volume, which is calculated based off of atomic radii. In general, this package has a bunch of descriptors calculates around 1,800 features of a molecule, and these features can range from just simple atomic count of number of carbons, number of sp3 carbons, to more complex descriptors, like more elaborate descriptors like Lipinski or the molecular volume. Another package that has been developed in quantifying molecular shape corresponds to Morphus, which was primarily developed for phosphine ligands, but I think it's being utilized for other molecules as well currently. And the different kinds of properties that you get from this package corresponds to, for example, the stereomole L, B1, B5, and then it also calculates, for example, the buried volume and additional features with respect to interactions, for example, the dispersion potential, which is the P-in feature. While Morphus and ModRad look into 3D aspects of a molecule, we wanted to take it a step ahead and try to look into how we could do multidimensional parameters in a vectorized fashion. And to do so, just looking at existing parameters, for example, the cone angle, which corresponds to the angle of this specific cone, or the buried volume, which is basically keeping an atom at the center of the sphere and quantifying how much percent of a molecule is present within the sphere of a specific radius, or the stereomole, as I just talked about in the previous slide. We wanted to move these into a more vectorized manner, by which what I mean is we want to look at how these specific parameters can vary for respect to proximal sterics or the distal sterics. So for example, if you want to quantify buried volume with respect to at a distance, for example, 5 angstroms away, the vectorized buried volume scans, which corresponds to looking at molecular volumes present in different concentric circles here, we would be able to say how much percent of a molecule is present just around the metal atom, for example, within this sphere, or how much percent of a molecule is present at a distance 5 angstrom away, for example, within this concentric shell. With respect to each shell, we could get out a feature vector which corresponds to shell 1, shell 2, shell 3, shell 4, for example. And this specific parameter is radial in nature. For example, you kind of calculate the molecular volume present at different radial shells. The other one that we'd like to look into with respect to vectorized features is the stereomole to vec parameter, which is just an extension on the stereomole. But here, what additional input features that we get is actually we can look at how the shape of the molecule varies along in this linear direction. So a traditional stereomole would just correspond to, for example, the length of the molecule at that specific atom center. But when we look at a vectorized form, we could say how the B phi and B1 parameter vary along a given direction. So you could get, for example, the curve of the molecular structure based off of the lengths along a specific direction. So this also provides a featurized vector in the form of what's present at angstrom 1 or at a specific distance, distance 2, distance 3, and distance 4, which corresponds to different points along this blue feature vector. So in general, these vectorized multidimensional descriptors essentially allows for understanding proximal and distal sterics, so which is close to a specific metal center, for example, or further away, and what plays a role in, for example, reactivity. So this is the background for DBStep, and how we could utilize DBStep is pretty simple. It's, first of all, it can be utilized with different kinds of input formats as shown, like listed here. And how for these specific input formats, DBStep could be invoked by just defining two specific atoms of interest. So for example, I have atom 1 corresponding to this carbon atom, and the direction that I want to look at for example, a steric measurement along this arrow, I define the second atom to be the atom on the ring. And then just having these two atoms, I can get steric measurements in terms of stereomole, for example, L along this ring, and then the B phi and B1 parameters. And then if I want to look at the volume, I could just invoke it using the argument of minus volume, which will give me the buried volume around this specific carbon atom, which is atom 1. Look into the more vectorized parameters. We essentially have to do a scan interval. For example, we have to specify what's the start position that we want to look at for the starting of the scan, and then the end and the specific step size. The step size corresponds to what's the size, for example, of the radial rings that we would want to exist. So just using, just defining two atoms and different parameters with respect to what you want to quantify, you could invoke this specific program in directly on the command line, or could also be incorporated as modules within Jupyter notebooks. One specific, I just wanted to highlight some examples of where this has been used. It has been used within our group to actually quantify radical persistence using buried volume. So as I mentioned, the buried volume corresponds to the volume of the molecule that's present within a sphere of, for example, radius 3.5. And when we look at quantifying radical persistence, we see that for a methyl radical, the value is just about 13% of the molecule, which kind of says it's very open to any kind of reaction, other reactions that can happen with, for example, another methyl radical or another solvent molecule that's present in the medium. But when we move to more sterically bulky substrates, for example, adding methyl groups on the carbon radicals, the number significantly increases to 38. And this can visually also be seen where there's a lot of molecular volume around the radical center. And when we move towards a very stable radical, which is known to have half-life of days, we see that for the nitrogen center, which is the radical center, the bulk of the molecule that's present around us is about 64%. And this nitrogen center is essentially shielded from any kind of potential side reactions that can take place. So this, using this specific parameter of buried volume, we were able to quantitatively understand radical persistence and come up with a radical stability score metric. Another application where these incorporations of stereomole to vec features was highlighted by the Segment Lab, where they tried to build linear regression models utilizing two different stereomole features. There were other features too, but I'm highlighting specifically the stereomole features here, which corresponds to the Bmax at, for example, the 2 angstrom position and the Bmax at 8.5 angstrom positions, which help them quantify the proximal sterics and the distal sterics, which was incorporated into a model to actually predict circular dichroism. And utilizing these two descriptors along with an electronic descriptor, they had a pretty good R squared of 0.91. So this was an application to identification of sensor materials. So there have been multiple other applications of this specific package as well. There's quite a lot of citations that could be found on GitHub, and I think having this package allows to actually study reactivity from a quantitative perspective, incorporating these vectorized features of stereomole and buried volume. With that was the first half of the talk. I want to